Welcome to today's lecture. We will continue with our discussion on the methodology for estimation of density and the construction of isochore for the aqueous carbonic inclusions from their total homogenization, the weight percent initial content in the aqueous component, density of the carbonic component obtained from the partial homogenization temperature. We were discussing about using the modified or the Redlich-Kwong equation, which is essentially a correction to the ideal gas equation. And since we are handling with liquid, but these equations are formulated in such a way from experimental data and from theoretical consideration of interaction of these molecules, that we can still use them in case of the liquids. And the only interesting thing about this particular mixture, the particular fluid mixture, is that the water, which is a polar molecule, carbon dioxide is non-polar. So, it actually involves interaction of the polar and non-polar molecule like carbon dioxide and water, and that is basically the reason why we have a substantial non-ideality in the system and immiscibility, a broad immiscibility field. So, the formulation will in any case be applicable within the limitations of miscibility in the region, and this also as we were discussing this equation, the formulation last class. So, here it is as we know that this is I equals to 1 to 2 and j equals to 1 to 2, and this is actually expanded as x 1 square a 1 plus x 2 square a 2 plus 2 x 1 x 2 into a 1 2. So, what do we get here? We get the terms which are the pressure correction term, we can call it the first non-ideal term, we can call B as the second non-ideal term. So, for the first non-ideal term we can get for the water as well as for carbon dioxide, and for carbon dioxide, considering it to be pure as methane free, these values are like as shown here, they can be calculated. So, now here for the first two terms we are using the pure first non-ideal term, but in the expression we get that there is a cross term which is a 1 2 which is coming here. That means, it is kind of a interaction term between these two components, water and carbon dioxide. So, this particular component is very easily could possibly have been very easily worked out by taking the product of the pure the intercept value, that the A0 of the aqueous component and the A0 of the carbonic component, and take a square root, and that could possibly have come from would have taken care of to give the cross term for the first non-ideal parameter, which is A. But the fact that these two species, water and carbon dioxide, they do react to give a product. So, this if we put H2O plus CO2 H2CO3, because of that their property, their PV-TX relationship will be affected by the degree to which this carbonic acid molecule will be formed. So, this carbonic acid molecule, in order to take care of that, we consider this reaction, this H2O plus CO2 H2CO3, and the equilibrium this particular reaction will have an equilibrium constant at and will be temperature dependent. So, this is kind of a equation which has been empirically fit as taking as the natural logarithm of the equilibrium constant as a function of temperature, where the temperature is in degree Kelvin. So, these formulations, actually some of them will be like the situation here, like the first non-ideal term, that is the A terms for carbon dioxide and water, are fitted as parameters into the functions of T, where the T is in degree Celsius. And here we are talking about the first component being the aqueous component, and the first non-ideal term of this A for H2O, which is also a function of temperature. Now, we are considering a pseudo binary. So, this water is actually not a pure water, this is charged with sodium chloride. So, this A of the first non-ideal term for water needs to be refined for taking into consideration the WNaCl, which has also been done. So, taking a simple case here of water and carbon dioxide, let us talk a situation where NaCl is 0. So, this will be the pure A term for water, pure A term for carbon dioxide, and they are expanded in this way. And this cross term, which is the by the interaction of the molecules of H2O CO2, which is put as AH2O CO2, is the square root of the product of the A0H2O and A0CO2 term plus a term containing the equilibrium constant R square T to the power 5 by 2 K, where ln K is a function of temperature. So, the purpose of giving you this little bit of an outline of the method is that this temperature, when we are considering, or these temperatures are all can be taken to be the temperature of total homogenization, because that is the temperature at which we are trying to calculate the molar volume, which will be exactly on the phase boundary where the homogenization has taken place. The system has actually become homogeneous. So, there we want to calculate the molar volume or the density. So, in all these formulations, this T in Kelvin or this T in degree Celsius are all temperature of total homogenization. So, it just gives us an idea that the amount of computation that we, or the calculations that we do, since these are many coefficient type of regression equation, and they need to the demand that we use a computer and use a computer code, so that we can process data of many inclusions, and their manual calculation will be very cumbersome and time consuming. Okay. Now, as discussed before, the Rayleigh-Combs equation, or when we are expanding the non-ideal term of A and B as a regression equations of temperature and weight percent NaCl, when we are considering a pseudo binary. So, there that equation can be expanded or can be written in a polynomial of molar volume. It will be a third degree polynomial considering containing term of VQ, V square, V, and the constant the coefficient terms will be involving pressure, temperature, and the A and B parameter. Like here. So, since we have, if we take the temperature and the R value is known, and if we want to reorganize, rewrite this equation as a cubic equation in V, then it will be something like A into V cube plus B into V square plus C into V plus D equals to 0. We can put in this kind of a form, and once if we put in this kind of a form, we will be in a position to solve this particular transcendental equation to solve for molar volume. But here there is a little bit of a trick involved, because this is a cubic equation in V. It will by conventional method of solution of this transcendental equation will result in 3 values of molar volume depending on what the situation is. So, here we use a judicious numerical method, so that we will be getting the root of this particular equation within a corresponding within putting a constraint, so that we get only one acceptable value, because as we know that 3 volumes for this 3 molar volumes for the particular fluid mixture is not acceptable if they come out to be all as positive integers, whereas it will only have one value which will be acceptable. So, we devise a appropriate numerical method in which we can solve, or we find out the root of this particular equation, which will be the molar volume of the fluid mixture. So, what essentially, as far as again I am coming back to this particular diagram. So, what essentially we do? So, when we start, we have the known parameter as temperature and only the WNaCl of the aqueous component, and then as said before, we are also going to use this particular equation for calculation of the volume fraction of carbon dioxide. So, what we do? So, here that means when we say that the fluid mixture at the homogenization condition will be falling on these isotherms on the PXCO2 pair. So, that means if we take certain assumptions of the carbon dioxide XCO2 in the system and then calculate the mole fractions of the other parameters like X or if you are considering only a pure carbon dioxide water system XH2 and XCO2, or if we are taking a pseudo binary with some fixed weight percent NaCl, then we can also calculate an XNaCl and H2O based on an initial guess or initial assumption of the mole fraction of carbon dioxide. So, the method in brief, which will be also be elaborated in the handout, that we start with an assumed value of pressure. Let us say that our inclusion has given as given a total homogenization temperature of 300 degrees Celsius. So, now what we do, we start with an assumed value of pressure. So, this pressure could be a judicious assumption, it could be anything between 500 to 2000, but we will start with an initial value, the lowest value, because we can see here that it is if we kind of take some combinations of pressure and XCO2, then we should be able to hit on one point on this solvers, which will actually give us the correct value or the consistent pressure and XCO2 value, which will be falling on the correct isotherm. But this exercise also does involve that once we have the temperature of homogenization, we could be in a position to construct such kind of an isotherm taking different combinations of the PXCO2, which is possible. Now, we start with an assumed value of pressure, and then with that pressure we also first start taking an assumed value of mole fraction of carbon dioxide. Let it be with a let it be start from a very low value of 0.001 or 0.005, or even we can consider such kind of a diagram and can also choose a value of XCO2. And now, with the known WNaCl of the aqueous component, we are calculating a set of mole fractions and we are solving the modified Redlich-Kwong equation for molar volume, which is which looks quite straightforward. Now, once we get the molar volume, we can convert this molar volume value to density value, because we have the molecular weight of these constituent components and the mole fractions, and from that this molar volume in terms of Cc could be Cc per mole can be converted to a density value of grams per Cc. So, that in that expression becomes our density of the inclusion, and already we have from standard formulation the density. So, what are the things which actually remain fixed in this condition? The parameters which remain fixed, which do not change, is the density of the aqueous liquid at the reference temperature that we have chosen. That reference temperature essentially will be corresponding to a homogeneous condition for the carbonic component. So, that particular reference temperature, this aqueous liquid density is known, and the temperature of homogenization is also one which we know. We always use that temperature, because that we are not varying. And then once we know the density, so we know the density of the aqueous component, we know the density here also, the density of the CO2 component, the d aqueous is known, T is known, and d of CO2 also at that reference temperature is also known. So, now what we can do is, with our assumed value of pressure and XCO2, we calculate the first term of the equation which we proposed there. It is the V of carbonic by the total V total, which actually is giving us the volume fraction. And as I said, this particular volume fraction can be converted into mole fraction by using a appropriate normalization procedure. So, now with the known density of the carbonic phase and the aqueous phase, a volume fraction V carb by V total, which can be calculated, and using the normalization procedure a new value of XCO2 can be calculated and checked for equivalence with assumed value. For example, what exactly I mean by that, suppose we get suppose we start with our XCO2, we decided that we will take a particular value of pressure, say for example, a pressure corresponding to this point, and it could be here as well, could starting from a low pressure or any pressure that we can think of. Sometimes in a computer, when we are writing a routine calculation procedure, we might always put the pressure variation in a regular manner with a pressure range, variation of range of the pressure, as well as for the carbon dioxide. So, for example, if we start from a point something here and here and here and here and here, then for each point, because that is not actually corresponding to the correct isotherm, but then on this point we should be able to get an XCO2, and that from the calculation that we have done, but that XCO2 will not be same as the XCO2 that we have taken as an assumption. So, only on points corresponding to this, talking it from a numerical point of view, if we are matching the assumed value of XCO2 and the calculated value of XCO2, which comes from by using the equation of the mass balance, the densities of the different phases is related. So, here this is the point on the isotherm which only will be situation where our assumed value of XCO2, or we can say that you can call it assumed or can initial guess. So, this assumed value of XCO2 would be equal to the calculated XCO2. The calculated XCO2 will come from the fraction, the volume fraction that we get in each stage, and then here we know that we have this calculation procedure actually has converged, and then it has given us. So, with the temperature known, it has given us a consistent or a acceptable value of P and XCO2, which would be falling on a correct isotherm. So, these are actually done by the procedure where we are comparing the XCO2 value that we calculated and the XCO2 value that we have assumed in the subsequent stages. So, as it looks like, it might so happen that in any particular chosen pressure, if we do this calculation, we might consume the entire range of initial gases of XCO2 without getting any convergence, and then we have to choose another pressure. So, this is in a kind of a nested kind of loop that we do the calculation for any chosen particular value of pressure. We take the entire range of our XCO2 initial gases and then check for equivalence of the assumed carbon dioxide mole fraction and the calculated carbon dioxide mole fraction, and if it does not converge, then we move on to another pressure with a pressure increment. So, in a routine calculation procedure, what we could possibly do, that XCO2 we could choose ranges of variation of pressure, let us say from 500 or say 200 bars to 2000 bars or 3000 bars, and the XCO2 from any of this the range. We can go from a 0.001 to 0.5 or 0.4 or 0.2 with an increment of 0.001. So, that only is making the calculation procedure only very intensive, but then this is the way that it could be achieved. Okay. So, now so this procedure is going to give us an acceptable value of the molar volume, or in turn the density of the mixture, fluid mixture, which is either a pure water plus carbon dioxide, or it is a water charged with electrolyte and carbon dioxide. So, it is a representing a pseudo binary of the ternary, and then we can. So, once we know the molar volume, we can calculate the slope of the isochore by taking the dP by dt value, or just calculate pressure at any other temperature, any other temperature value, and can get the isochore as shown from the series of diagrams where the isochores could be plotted. But then we must also be aware of the limitations of this particular method. First of all, it is actually just semi empirical in nature, some theoretical considerations and empirical fitting to observed experimental data, and in fact, this system, this NaCl H2O and NaCl CO2 H2O system, the experimental data is rather limited, and the formulation that was proposed in the literature, which the references which will be given, these are quite old now. There are many new methods, new formulations which have been proposed by many different workers, which can also be consulted, but these have this approach of using a modified Redlich-Kwong type equation has been quite popular. But this here is that the original data set from which these equations were formulated were very limited on their ranges of compositions, although it is applicable. As you can see here, this equation sets that we have discussed is applicable from 350 to 600 degrees Celsius and any pressures higher than 500 bars. That means, if we get, which is of course very unlikely, if we get a total pressure of homogenization of a carbon dioxide H2O inclusion, if it comes out to be less than 500 bars, then it will always raise a question that it possibly has gone beyond the range of applicability, and the temperature similarly here is 350 to 600 degrees Celsius and NaCl weight percent of 35. Although it is said, but then the data points towards the higher concentration of NaCl has been rather sparse, and there are many other refinement. So, refinement to this particular, the phase relations in this particular ternary has been a very challenging job, and also there has been many attempts even till now, being this particular system is being attempted to be formulated, and better acceptable equations of state to be proposed, so that better, more accurate and more refined values of the density and the isochores could be calculated. Now, here this also there is another situation here, that the applicability of this particular equation state is only to a situation where the carbon dioxide, where the homogenization is to a liquid phase. Means we can very well apply when the homogenization process is L aqueous plus L carbonic to L aqueous. So, its applicability is to homogenization to carbonic phase is a little bit of, there is some amount of some uncertainty which involves. And then, as said before, this gives the minimum pressure of entrapment. Means when we want to calculate the pressure of formation of this particular mineral or the temperature pressure condition of the fluid, then we can only approximate it to the minimum pressure of entrapment, because we know that actually it is falling on. So, we are, as we saw before. So, it is actually falling on these where the inclusion could have been trapped anywhere in the one phase region. So, there is one of the limitations also, that it gives the minimum pressure of entrapment. Okay. So, now let us discuss about the thermobarometry with this kind of mixed aqueous carbonic inclusion. And in this, as per our general understanding of the entrapment of homogeneous fluid and its evolution and post entrapment phase changes that happens after the entrapment. So, the case 1 here, whether we will be able to do the thermobarometry with mixed aqueous carbonic inclusions. We will see the case 1 is simple, it is general idea that the entrapment takes place anywhere on an isochore. Entrapment takes place anywhere on this isochore, and which we are only able to constrain this temperature pressure value corresponding to our total homogenization of this mixed aqueous carbonic inclusion. So, that means we would be able to get only a pressure which is the minimum pressure minimum, and also this temperature at which the homogenization has taken place, this also temperature minimum. And normally as we see these mixed aqueous, because the carbon dioxide content in water at any particular temperature will always result in density decreasing. So, here we see that the density of the isochores are also dP by dt value is also goes to lower and lower values, and just as we consider in case of our aqueous inclusions, it also can be thought of exactly as a pressure correction. If we are doing this exercise on a metamorphic rock, and where in our mineral assemblies, which we will be also be discussing in some degree of we will elaborate the discussion on the when we discuss about applicability to metamorphic rocks. So, if we are working on fluid inclusions in a mineral which is a part of an assemblage which gives us a good barometer, then in that condition suppose we know what is the pressure, and then we can always see that pressure on the isochore we drop a perpendicular and can get the temperature, and this is also exactly the pressure correction that we discussed in case of the aqueous biphase inclusion. So, in similar case, so once we this particular isochore in case of the mixed aqueous carbonic inclusion is calculated on the basis of the same MRK equation, because the same values of A and B parameters we can use for a temperature of homogenization, and the molar volume that we have conversed with the pressure and molar volume. So, we can calculate the pressure at any other temperature for, because we know that on this particular isochore the molar volume is remaining constant. So, once we construct the isochore, we can also get the similar situation, then get the true temperature of trapping of this homogeneous aqueous carbonic fluid, and can do thermobarometry. So, we will continue discussing on the thermobarometry of this mixed aqueous carbonic inclusion in the next class. Thank you.